All right, today we're talking about subsets. All right, so we y'all can obviously read the little backstory about subsets and tattoos if you feel like it. But here's the crux of it. Here are subsets. So let's actually take this out. Something about this textbook doesn't seem to jive well with this um, blackboard. It covers my stuff up. My other classes don't do this. Alrighty, so the definition of a subset of a set. So we're gonna have two sets. We're gonna have two sets. One set's called A, one set's called B. Okay. Set A is gonna be called a subset of B, right? Now, first of all, yeah. First of all, if you were to try and just on context clues describe what a subset is, well, you would think, okay, well, subset, sub, beneath, and then set. So it's a set that's beneath the set, right? So that's all this really is. So set A is a subset of set B expressed as A, and then this little symbol here is the subset symbol. So the subset symbol is just basically, so you know how you have your less thans, right? The subset is just basically a rounded version of it, just like that. And then this, okay? And then you could think of it as the or equal to sign, and we'll see something here in a moment where we get rid of that sign. But that's the subset symbol. It's just basically a subset is just a little round and like that. Okay, kind of like a C that's underlined, right? And of course that is for if every element in set A is also an element in set B. Okay, so for example, if we were to apply this definition to the set of people ages 25 to 29, so the set of tattooed Americans in the 25 to 29 age group, okay, we write that in set builder notation, X such that X is a tattooed American and X is between 25 and 29, right? That is a subset of X such that X is a tattooed American. Okay, that makes sense, all right? Because if we talk about tattooed Americans, I mean, the tattooed Americans they're tattooed of all ages, right? But this particular number here is specifically for the age group 25 to 29, including 25 and including 29. So we can see how this is a subset of that. Observe that a subset is itself a set. So the notation A, and then we remember our subset symbol here. If we put a line through it, that means not. Okay, it means not a subset. So the notation A not a subset of B means A is not a subset of B. Set A is not a subset of set B if there is at least one element in set A that is not an element of set B. For example, consider the following sets. Okay, we have set 1, A2, 3. I'm sorry, set 1, set A, 1, 2, 3, and set B, 1, 2. Okay, you can see that A is not an element of a subset of B. Okay, because we have the element 3, and 3 is not in B. So A is not a subset of B. However, we can say that B is a subset of A. Notice how every element in B is also in A. So B is an element of, I'm sorry, B is a subset of A, but A is not a subset of B. I feel like I might have butchered that somewhere, and if I did, just read the text. That's a lot easier. I know I said some things there. I'm sorry. Hopefully I didn't get too tongue-tied or mess up there. All right, so let's do some examples. Actually, I'll start put it over here. Okay, so A, write. We are asked to write a subset or not a subset. Okay, and then we're going from A to B. Is A a subset of B or is A not a subset of B? So looking at A, We have the set A contains the elements 1, 3, 5, and 7. Set B contains the elements 1, 3, 5, 7, 9, 11. So every element in set A is an element in set B. So therefore, we will say that set A is a subset of set B. Okay, and again, it's just kind of filling in these. We're going to be filling in these blanks here. But I guess here's what I'll do. I'll just go ahead and just write the context there. A is a subset of set B. Okay. Now B, we have A is the set X, where X is a letter in the word proof. So the set A is P-R-O-O-F. Set B is Y, such that Y is a letter in the word roof, R-O-O-F. Okay. Well, right away we can see that set A has has the letter P, and therefore set A is not going to be a subset of B. Okay. And and we're going to problem C. Set A is X, such that X is a planet of Earth's solar system. And B is, well, it's all the planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Okay. So these are the same sets, right? But as mentioned on the previous page, a set is a subset of itself. So we can say that yes, A is indeed a subset of set B. Okay, so a moment ago I mentioned that we can kind of think of this as the less than symbol. Well, we can say that because we also have the equal to and then a not equal to. So before I get ahead of myself, let's go ahead and take everything out here. All right. So starting on the left, proper subsets. So in example 1C and checkpoint 1C, so example 1C, we noticed that they were the exact same, right? Both sets were the exact same. So the given sets are equal and illustrate that every set is a subset of itself. If set A is any set, and A is a subset of A because it is obvious that each element of A is a member of A. Makes sense? If we know that set A is a subset of set B and we exclude the possibility of the sets being equal, then A is called a proper subset. Okay, a proper subset is written with the C, the weird looking C, but without the equal to sign, right? So right now, or up to now, the subset looked like this, and that was, this horizontal line here kind of meant, same thing as, less than or equal to, right? Kind of meant the same thing. Well, if they are not equal to one another, then we would call it a proper subset. Okay, so for example, going back to these, the example one, A and A, sorry, just A, just A is a proper subset of B. Okay, so every element in A is in B, and set A and set B are not equal to one another. So we could say that it is a proper subset. Okay, so the definition I pretty much went over it, but we'll go over it again. So set A is a proper subset of set B expressed as A is a subset of B if set A is a subset of set B and sets A and B are not equal. Okay. And of course, we saw the example on the previous page, but here's some more examples. Set A is a subset of set B. It is true. It is a subset, but it is also a proper subset. Okay, we have the and word in there. So it is a subset and it's a proper subset. So by contrast, there are subset examples where only the symbol subset can be placed between the sets. So set A and set B, only this symbol will work, right? Because these are the exact same sets and they're equal to one another. One set is not a subset of the other. It's not a proper subset. Man, this is going to get tongue-tying really quick. Okay, so example 2, we are asked to write uh, subset or proper subset or both in each blank to form a true statement. Okay, so statement 1 is set A is the set X such that X is a person that lives in San Francisco. Set B is X such that a person lives in California. Okay, so we can say both that, oh yeah, let's try to be a little consistent there. Let's put it on the right. We can say that A, we could use both of them, right? Because somebody living in San Francisco does indeed live in California, okay? And somebody living in San Francisco, uh, people living in San Francisco is a subset, a proper subset, right? Because obviously there's people living in a lot of places in California, but those living in San Francisco is a proper subset of those living in California. And B, so set A is 2468 and set B is also 2468, just rearranged 2846. Okay, so the only symbol we can use here is this symbol because they are equal to one another. Right? We can only use the subset symbol because again, a set can be a subset of itself if it's the exact subset. That's the only symbol that we can use there. Right? So subsets and the empty set. The meaning of A is a subset of B leads to some interesting properties of empty sets. All right, so looking at example 3, set A is the empty set, and set B are is the set with elements 1, 2, 3, 4, and 5. This is asking, is A subset of B? Okay, so our definition earlier is that A is not going to be a subset of B if there's at least one element in A that is not an element in B. Okay, we don't see that. Okay, now the empty set is just basically like an empty room. Okay, I mean you call a room empty even though there might be air in there, right? So the empty set is just there's no elements in it. So we can say in this particular case that yes, yes, A is a subset of B. Okay. And then we'll talk more about the empty set. Alrighty, so looking at the top, the empty set as a subset. For any set B, the empty set is going to be a subset of B. So pretty much every in any set, we'll have the empty set as a subset. Okay. Also, for any set B other than the empty set, so as long as B is a set that is not the empty set is going to be a proper subset of B. Okay. So on top of our solution here, right, it asks, is A a subset of B? Well, it is also a proper subset. Okay, so let's put that down as well. It didn't ask for it, but we're going to put it anyways. Also, A is a proper subset of B. Oh, sorry about that. All right, so the number of excuse me, the number of subsets of a given set. One moment. All right, if a set contains n elements, so that means n number of elements, how many distinct subsets can be formed? So let's observe some special cases, namely sets with 0, 1, 2, and 3 elements. We can use inductive reasoning. So going back to the very first lecture here, but inductive reasoning. So basically, we're going to be going off of what we observe, and we're going to make a reasonable hypothesis, right? So we can use inductive reasoning to arrive at a general conclusion. We begin by listing subsets and counting the number of subsets in our list. Okay, so the empty set, right? It has no elements, 0 elements. This is what it looks like. It's just, again, just plain old empty. There's nothing there. And it has one subset, okay, which is the empty set, right? It's equal to itself. This set has the element A in it. That's one element. And list of all distinct subsets. Well, A is 1, and the empty set is also 1. So that makes 2. And then we have A and B. There are 2 elements, and we can list all the subsets. AB is a subset, A is a subset, B is a subset, and the empty set is a subset. And that makes 4. Okay. A, B, and C, the sets A, B, and C, it has 3 elements. Okay. It can be arranged as ABC, AB, AC, BC, A, B, C, and empty set. These are all the possible subsets of the set ABC, and there are 8 of them. So what we're going to do here is some of you can possibly know what the correlation here is, right? 1, 2, 4, 8. Well, I would postulate that the next one would be 16. There would be, if we had A, B, C, D, if we had a set of A, B, C, and D, I bet there would be 16 elements in it. Okay, of course, I know that because I've done this before, but looking at this pattern, I know the pattern because that is basically the pattern of 2, the base of 2, raised to the first power, which is 2, 2 squared, which is 4, 2 cubed, which is 8, and then 2 to the 4th will be 16. Okay, and of course, that is what we observe down here. Okay, the pattern is just 2 raised to the nth power, and I'm pretty sure we'll expand on that here in a moment. Okay, so we're going to put, I wonder if I can put this on the same page. I feel like it's good stuff. Put this over here, put this right here, and I don't, no, let's see. Can this fit somewhere? Looks like I can fit it right there. Nice. I'm not cutting off anything in the definition down there. We're good. Perfect. All right. So, oh no, I cut off the top there. There we go. So, the power of 2 is the same as the number of elements in the set. Using inductive reasoning, if the set contains n elements, then the number of subsets that can be formed is 2 to the nth power. So that n is however many elements are in that set. Of course, that is restated here. So for a given set, we know that every subset except the set itself is a proper subset. So every set, so let's look back here. Every single one of these sets except the set itself. So for this one, the set itself is A. That's the set itself. AB, that's the set itself, and ABC is the set itself. Where was that? We know that every subset except the set itself is a proper subset. In Table 4, we included the set itself when counting the number of subsets. So in this set, we included the set itself. We must exclude counting the given set, thereby decreasing the number by 1. So the number of proper subsets is basically just the number 2n and then minus 1. So in this particular case, it's 0. In this particular case, it's 1. In this case, it's 3. In this case, it's 7. You just subtract 1. And then over here to the right is a brief review of the powers of 2. Admittedly, I mean, if I thought about it, I can definitely go, let's move this out of the way. I could definitely go beyond 2 to the 10th power because, I mean, well, especially maybe the 11th, maybe 12th. I can definitely memorize 11th to the 12th, but 2 to the 10th power is what I can quickly memorize and spout out, mainly because these numbers are numbers you associate with data sizes. For this class, and probably any other math class that you'll be taking, I would say 2 to the 6th power might be the one up to the ones you need to memorize. Maybe up to 2 to the 8th power. Okay, but again, if you're familiar with data sizes, you could easily say, okay, 64, 128, 256, 512, and 1024, right? We just double it each time. So you could probably quickly come up with that. But I would suggest memorizing up to 2 to the 6th, maybe 2 to the 8th power. And honestly, if you're there, just make the jump to 2 to the 10th. Okay, so A, find the number of distinct subsets of the number of and the number of distinct proper subsets for each set. Okay, so for A, that set has 5 elements. All right, well, 2 to the 5th power is 32. So there are 32 subsets. 32. I'm messing that up. Sorry. 32 subsets. And then there will be 31 proper subsets. So 31 proper subsets. And for the record, my handwriting is way better than this. It's just writing on the tablet. It's a little rough, right? But anyways, that's how that's done. All right. And B, there are 7 elements. Okay. So 2 to the 7th power, I know is 128. So there are 128 subsets and 127 proper subsets. Right? And that's it, right? All I do is I said, okay, there's 5 here, there's 7 here. So 2 to the 5th power is 32, and 2 to the 7th power is 128. Yeah, whew, that was a close one. Yeah, 2 to the 7th power is indeed 128, right? All right. That concludes the lecture, but I will snip this a little bit about infinite sets. I feel like it's interesting, especially because I feel like uh, talking about and playing with infinities is kind of fun. We do that. Well, heck, we're doing that in calculus right now. So if you get the itch, you can check out those videos. Okay, that's it. All right, that concludes today's lecture.